All right, so hello. So today we're going to go over our last topic for the unit, which is electron configuration. Okay, and so what we really want to do here is use electron configuration to see what the periodic table indicates about the arrangement of electrons. Okay, so there's a lot of information on the periodic table that can give us some information about our arrangement of electrons. And so we've already seen one representation of electrons in the shell model. Okay? The problem with the shell model is it's really oversimplified. Okay? So it's not a good depiction of what an atom is really like. And the reason why is because our electrons are not spinning on rings like we show in that model. There's not these fixed rings where our electrons are. And actually, the problem would be that, okay, if our electrons were actually on this rings that were spinning around this nucleus, eventually, according to physics, they would accelerate and eventually crash into the nucleus. And so you can imagine if that happened, then, well, we would have no more electrons and thus no more atoms. All right, so there has to be something else. The shell model can't be how our atoms really are. All right. So why do we teach this shell model? Well, it's a good intro. Okay, so it helps us easily understand where our electrons generally are, and then say, okay, which ones are core and which ones are valence. Okay, so it's a good starting point. But we need something a little bit more. Okay, so as we get deeper into the course, we need something that gives us more information. And that something is electron configuration. And so it allows us to confidently understand the location of electrons. So this isn't just a generalization anymore. This actually tells us specifically where they are. All right. And so what electron configuration is a way to keep track of all the electrons in an atom or an element. Okay. And it includes three pieces of key information. The first is where are all the electrons located? All right. So it tells us where they are. The next is what energy level are our electrons in? And the third is what orbital are our electrons in? And so we'll get into what an orbital is in a little bit. But again, if we look at the shell model, all we really see are electrons on rings. If we use electron configuration, we can get these three pieces of information. But there are things that we can take from the shell model that help us out, okay, as we start to draw electron configurations. One of them is that we use the periodic table to find out, okay, how many electrons do we have in an element? So say you want to draw the shell model of carbon. So carbon is in our red box here. And so it shows you, okay, our atomic mass is about 12 and our mass number, or our atomic number is 6. Okay, so that tells us we have about 6 protons, 6 neutrons, and 6 electrons. And so when we drew our shell model, we drew our 6 electrons on rings. And so we saw that, okay, 2 electrons could fit on the first ring, and then up to 8 could fit on the second ring. So in this case, we have 4 on the second ring. All right, so again, this was a good kind of intro, but it is a simplification. And so why it's a simplification is that the periodic table is actually organized into sub-shell blocks. So there's a lot more information that the periodic table can tell us. All right, and so when we think about what these sub-shell blocks are, they involve numbers and letters. So you see there's like a 1s here, a 2s here, down here is like 3d. And so what happens is all the letters, the area where the letters are the same, so like these are all s's, we call the s block. This is the d block, this is the p block, and down here is the f block. All right. And so again, we'll go into a little bit more about what that actually means a little bit later. But we can use this information, this organization, to help us write electron configurations. And so what we want to do is start by writing the electron configuration of carbon. So again, here's our shell model of carbon down here. And so, well, what did we do to make that? Well, we looked to see where carbon was on the periodic table. All right, and so what I did here is I took out a lot of the periodic table. And the reason why is that we're really only going to be using this top half. Okay? I'm not going to give you elements that are way down in the bottom. All right. But this is where carbon was on the periodic table. All right. So all I've done here is I've taken out the numbers on the periodic table and I've just left in our blocks, our subshell blocks. And so once you do that, all you're really doing is counting boxes. And so we have 6 electrons, okay? And so what that means is that we want to look and see, okay, where are our 6 boxes? Well, here's 1s1, okay? Then we're at 1s2, okay, so there's 2 1s's. Then we're at 2s's, so 2s1, 2s2, 2p1, and 2p2, right? So again, this is what an electron configuration looks like. Okay? So again, how did we find that? Well, you have to remember that we read it from left to right. Okay. So from 1s over here, I jumped over here. And then I went here to 2s. And then I jumped over to 2p. And again, what you do is you look and see, okay, what is the what's the number, what's the letter, and then how many boxes do you have? And the boxes you write as this superscript. So here I had 1s, right? So here in 1s, I had 2 boxes, so I write 1s with 2 as a superscript. Then I'm at 2s, and I have 2 boxes, okay? So I write 2s with 2 as a superscript. And then over here, I'm in 2p, and how many boxes do I have? 2. So I write 2p with 2 as the superscript. And again, how I write the electron configuration is I just write that all out together. All right. And so what does each of these things actually mean? Well, so this coefficient here, the big number, tells us the energy level. So this tells us, okay, what energy level are our electrons in? And so the higher the number, the higher in energy the level is. All right. The letter, so in this case it's either S and P, or S or P, tells us the orbital. Okay. So again, in a second I'm going to show you what an orbital actually is. And then the superscript, like we saw on the last slide, tells us how many electrons there are. So in the last one we counted boxes. Those boxes you can say represent electrons. And so these superscripts will tell us how many electrons are in each subshell. And a little trick to knowing if you did it right is that your sum of the superscripts, so if you add them all up, should equal the number of electrons that you want, which if our atom is neutral is also the atomic number. So again, the atomic number for carbon was 6, and we had 6 electrons. So if we do 2 plus 2 plus 2, we get 6 electrons. All right? And so what are orbitals? Well, remember the orbitals are what is told to us by these letters. So we saw S and P there. There's also D and F, but we're not really going to go into them. You can see they're a bit more complicated. But what the orbitals are regions where our electrons are. Okay, and so they come in all these different shapes. Okay, so instead of having, like a fixed ring like we did in the shell model, we have these orbitals where our electrons are actually hanging out. And where we see the little shapes is where within our electrons are. So there's a probability or high probability that our electrons are going to be in there. Okay, so again, all these orbitals are just these shapes where our electrons are. So there's not much that you need to know about these. You don't need to know how to draw them or anything. I just want you to know, okay, what do our letters actually mean? So if we do another example here, let's do sodium. So sodium is down here. Okay. And again, what we want to do is we want to be like, okay, so sodium is down here. That means it has an atomic number of 11, and its mass is about 23. Okay. So what does that tell us? It tells us we have 11 protons and 12 neutrons. Right? If we have 11 protons and we're neutral, it also means we have 11 electrons. Right? And so there should be 11 boxes that we count. Right? So over here, I'm in 1s. So how many boxes do I have? 2. All right. And now I'm down to 2s. How many boxes do I have? 2. And then again, we read to left to right. So I jump over here. Now I'm in 2p. How many boxes are over here? Well, there's 6. And now I'm at where I want to be, which is sodium. And how many boxes do I have here? Well, there's only one of them, and it's 3s. So how would I write that? I would write it as 1s2, 2s2, 2p6, 3s1. Again, because in 1s, I have 2 boxes. In 2s, I have 2 boxes. In 2p, I have 6 boxes. And in 3s, I just have 1 box. And again, what do those boxes represent? They represent electrons. So again, if I add up these superscripts, I get 11. So I get 11 electrons. Okay. And so there's another way that you can write this, which is known as shorthand or noble gas notation. Okay, so you can use either, I don't care. So if you like the first way I showed you, that's fine. If you understand this way that I tell you now, you can also use it. This one's just a little bit faster. All right, and so why it's a bit faster is because it uses the nearest noble gas. And so the noble gases are our last column on the periodic table. So what you do is you find the noble gas that is closest to whatever element you're looking for with a lower atomic number, and then you fill in the rest. So again, this is going to be a little bit hard to see without showing you the location. I'm going to show you the location in a second. But say I wanted to draw an electron configuration of silicon versus neon. Notice that this part that's in blue is identical. Okay, so this blue part is actually my electron configuration of neon. And so what I can do in shorthand notation is be like, okay, well, if that's the same, I can just summarize it by putting that in a box. And so I do that by putting it in brackets. And so my shorthand notation puts the symbol for neon, which is Ne, in brackets, and then whatever remaining electrons I have. So the non-blue part here. And so again, how it works is I look for my noble gases, which is where this arrow is. And again, the one I was looking for was silicon. Okay, so that was what I was asked to find the electron configuration of. So you can either do it by doing what we did before, which is just counting up all the boxes, or you can be like, okay, silicon is here. Where's the closest noble gas with a lower atomic number? Well, that would be neon. All right, so remember, you want to have the lower atomic number, so don't use argon because it has a higher atomic number. So we'd want to go to neon, and then you can put neon in brackets, so you would put the Ne in brackets, and then just be like, okay, this is 3s, so 3s1, 3s2, and now I'm in 3p. How many boxes do I have? 1, 2. So I get back to this here, where it's, my fingers away, where it's Ne in brackets and 3s2 and 3p6. Right. And so again, all I did there was I took the part that was the same in silicon and neon, I took it out. I represented that by putting the neon Ne in brackets, and then had the 3s2 and the 3p2. So that was what was left, all right, our remaining electrons. Okay, so this can be a little bit tricky when you see it at first, so definitely, ask questions if you need to. But how we're going to practice this is through a Moodle quiz. Make sure you read the directions because they're a little bit confusing, okay? And the reason why is because remember, you can choose which configuration you write. So you need to use the full one or the shorthand one. So there's spaces for each. And so what you're going to do is the one that you don't use, you're just going to put an X in it. And again, it's going to show you that it's wrong, but I'm not going to count. I'm not going to take points off for you. So even though that it's going to take points off on Moodle, you won't take points off on Aspen. But again, if you have questions about any of this stuff, I'll be on the Google Meet. So just make sure you come back and ask. All right.